So I'm Christian from Intel. I will tell you, what is still our journey to onboard the VNF. And the VNF for us is an EPC, an Evolved Packet Core. So this is work with a lot of people from Intel, a lot of people from ON Lab. Of course, you always forget the most important one, people from Sprint. And Lyle here has been the lead architect on some of this work. Some legal stuff. So we'll tell you briefly what is what we call a NGIC, a Next Generation Infrastructure Core, which is an EPC, and what has been the process of onboarding NGIC onto M-Cord. So NGIC is an EPC which is available on the Cord Git, the repository. You have the Gerrit here URL. Today, what is available is an S and P gateway, service gateway and packet gateway. We are adding other components like the MME, HSS, and PCRF over time, and hopefully soon. Right? For us, it has been a research and collaboration process with industry partners, AT&T, Sprint, to understand how telecom workload would run on off-the-shelf servers, Intel architecture servers, going from dedicated hardware devices to general-purpose CPUs. We have released, the learning and this optimized reference software again into Cord. It is not a product from us, and probably will never be at least one from Intel. But again, we'd like the community to work on it and improve it. There will be detailed presentations about the NGIC architecture, its performance, its capability on Thursday morning at 10 in the next room, as well as the hands-on tutorial also on Thursday on how to run NGIC. You'll see in a containerized environment. For people who want to attend the Thursday session and wants to be ready, you can go and install Docker, at least 1.13, install Docker Compose, and pull some Docker images, and then you'll be ready for the hands-on session, right? So what is NGIC, right? You have here a view of the system component. There are about the 5 components of the EPC. We have the service and packet gateway user plane, which is either a process, a VM, or a container. I mean, running on bare metal in a VM or container. You have the control plane, which is separated from the data plane. We have a disaggregated EPC. We did a lot of evaluation over the last few years to try to learn, what were the bottlenecks of what we can call traditional EPC, where control and data plane are kind of merged together. And finally, we decided to disaggregate control from data, following, the SDN model. One talk to the other through some interfaces. We used OpenFlow 1.3 in the past. We use 0MQ now. I mean, we are kind of transport independent here. We have used different transport protocol. What this allows us to do, as compared to the previous architecture, where previously, if you need to scale your EPC because you're out of resources on the control or out of resources on data plane, you're gonna scale a big block, and maybe you're oversubscribed on your data plane. And people don't have to have, to lose capacity, to have unused capacity. Having a disaggregated EPC, we can scale them independently. If I need more control, I'll scale the control. If I need more data, I'll scale the data. And you can have, an N to M communication, N control plane to M data planes. That was one aspect. Other aspect, we did optimize the data plane to follow, a match action semantic. It's done in software, but this is like what an OpenFlow switch would be doing. So the pipeline stages of the EPC from, NCAP, DCAP, bearer mapping, metering, quality of service, any type of processing of the pipeline follows a match action semantic. We did a lot of work also to optimize lookup done on the Intel architecture have very efficient lookup with very large table. So some of the software also has been released as part of DPDK, which is an Intel optimized library. It's open source. It's all available. And as I mentioned, we had this independent and scalable control and data. So in kind of dark blue, these are the components which are available today on the code repository. Light gray, these are the components which will be coming, in the next few months. As a RAN, we have been using multiple RAN emulators. Here we show Spearant Landslide. We have also used NG40. We know we talked with Ixia also, and I think in some of our partners, they have been talking with a real eNode B, with a Nokia eNode B. So the software has been exercised with various RAN, we could say. So I guess today you heard a lot about CORD. What is CORD? Of course, open source. That's one of their goals. But disaggregation of workload, and we show you how we did disaggregate control and data, at least for the EPC. Virtualization. We run in a virtualized environment. We run as bare metal, or we run as container. Cloudification. How do you have anything in the CORD environment from OpenStack and the other component to allow you to work as a cloud environment. And programmability, again, by separating control from data and having open interfaces, anyone could come and program the device, knowing what are the APIs. Okay, so now we had the EPC. It's running, let's say, as a bare metal service. It's running as an independent processes. How do we move it into the CORD environment, right? How do we onboard the EPC? So first, we had to learn about CORD. There's a lot of software with CORD, right? OpenStack, XOS, ONOS, VTN, virtual tenant networking. How does this work, right? And so for us, the easiest way to start was to work with CORD in a box, which is available, on Cloud Lab. You can go, you can work on it, you create your environment. And that was, an easy setup. You don't have to build a physical pod, right? And if you build also a physical pod, depending where are the services, you might have to deal with your corporate firewall, which for us was, a real problem also inside Intel if we had services outside of the corporation. So it enables you to get very familiar with the CORD environment. The drawback for us was the VNF we had required significant system resources. For example, on a data plane with a certain number of core, CPU cores, right? 6 to 8 cores, or depending upon the type of traffic you would like to see. We also require system memory. And CORD in a box has fairly limited system resources available to you. So what we did, to learn how the system works in CORD in a box, we use simpler VNF. We use, L2 forward or L3 forward VNF. So we were able to onboard the VNF, connect them together, have traffic go through. And this gave us an idea of what is a CORD environment. But clearly, we were not able to run the EPC as we have it in a CORD in a box, right? But I think it's definitely the way to start with CORD, right? So then we say, well, we have to bite the bullet and build a physical pod of CORD, right? So we have, few servers, we have the switches, and we have, various servers running what is required for CORD, right? The head node, right? The head node running, XOS, running OpenStack, running, VTN, and then a set of servers, compute node, which will run the EPC, right? So for first phase, which was by the Open Networking Summit in April of this year, we use the GUI by hand to create, the slices, to create the virtual networks, and to instantiate the VM, and stitch them together to run them, right? So they were running in the core environment, but there were no automation. So that was all running, right? VMs were created. We stitch them together and we send traffic through, right? So this was the first step, again, back in the Open Networking Summit. Then a few months ago, by MWC America, we made, further progress, right? We've progressed further. By this time, we used XOS to automate the creation of the slices and the virtual network using, Tosca description files. Then we still use the GUI to instantiate the VM by hand and to stitch them together. So, it takes time. But, again, we were working in the core environment. We added, some more automation with the XOS aspect. And, we had less work to do by hand, right? And then, as of core build, and actually as of last night, so, very, very close, we have full automation using XOS, which now creates services on top of the previously created slices and network, right? It provides, automation to instantiate, to set up the application inside the VM, right? Inside the VM, for example, we have the control plane and the data plane. They need to have, IP addresses assigned to their interfaces so they can talk to each other. There is a certain configuration for each process. And we do all this now through XOS, right? So we start to have, a fully automated service up and running. That's what they call, Larry called earlier, EPC as a service, right? So this is, brand new, and you can probably see it working tomorrow or next day, right? There are like 2 booths out there. I know ONF has a booth with Ping. They'll show some of the EPC running in the core environment. We do have a booth with Spirant, and you're going to see some, the EPC operating by itself, basically. Right? So, yeah, as of today, you have, a fully automated and orchestrated EPC available in MCORD, right? Now, what did we learn going through this, right? And we learned a lot. And there was still a lot of work that needs to be done, a lot of optimization that needs to happen, right? So what are, various deployment models? And you'll see, some of our learning. So in this case, for example, here, all the services, including, the inode B and the application servers, are part of the tenant. So they are known to Cord. Cord knows the IP addresses of, all these interfaces. Everybody is in the same box, if you want, right? So that seems, to be one of the easiest model. However, to do this, you need to create what we call, a very simple L2 virtual network connectivity, which is a little bit different from the one available at the default on Cord today. The Cord private type network, virtual network today, does a little bit more than L2 connectivity only. It also prevents, L3 anti-spoofing. Well, what happened? When you have encapsulated packet, which is your UE packet, your user element packet, your phone, when the packet is going to be decapsulated outside of the user plane going to the application server, this guy over there doesn't have the same IP address, and the rules of the L3 anti-spoofing will drop the packet, basically. So your packet will never reach the other side. So we have to go and modify a little bit the rules here by hand, right? It's easy, but it has to be done. So we'd like to create a new type of L2 private network, very simple one, which does only L2, right? And everything will go through the pipe, right? Otherwise, as an alternate solution, your VNF needs to implement a NAT inside the VNF. That might be okay if you develop the VNF right now, but if you want to support a legacy VNF which doesn't have NAT, you need to have, this as a type of virtual networking, simple virtual networking, right? If you guys have any question also along the way, please feel free to ask, right? Another type of model that we have, and this one might be closer to reality. I don't know, a mix of both, right? Where some of the services are outside of the tenant or outside of what Cord manages. So Cord doesn't know the IP addresses of the A node B, and doesn't know the IP addresses of the application servers, right? And here, we might ask operators, what is the right model? Maybe the E node B here is part of Cord, but not the application servers. If you want to reach, CNN.com or any other stuff, these guys will be definitely outside of your control. But you might control the E node B, right? Well, in this case, you need to discover these addresses, right? And you need to tell automatically. Today, we still do it by hand here. We force some ARP entries in the various modules so traffic can go through, right? But it would be nice to, automatically expose these other IP addresses, like you see, S1 AP, which is between the E node B and the MME. In this case, MME here is inside Cord, and the E node B is outside of Cord, right? So we need to expose these addresses. And same with the SNP gateway, S1U, and SGI, right? This information need to be exposed to the outside world. And then the hardware switches and, vSwitch table need to be updated so the traffic can go through from the edge of the data center to the appropriate compute node, right? So today, we do it a little bit by hand. It would be nice to automate this further, right? You also need to add this, custom route in the vRouter, right? So the traffic, again, you have encapsulated traffic on one side on the E node B. This traffic will be decapsulated when it goes through the SNP gateway to reach the internet. The vRouter needs to know how to send back traffic when the traffic comes back to the E node, to the UEs, right? So you need to add, some of this routing information inside the vRouter, inside the environment. So, there is some additional automation that need to happen. And here again, it would be great to hear from operators what is the most appropriate model, what is the right model. So, Cord could focus on, making it as easy or as automated as possible for the right model, right? And maybe it's, we need to have the flexibility to support any type and to combine any models, right? No questions? It's very clear.
Who's controlling the vRouter? Is
Well,
it OS or?
That's a good question, right? Do you control it in your data center or is it in the owner's control? Yeah. But we'd like to hear from you guys what's the right deployment model. Okay. Another stuff that we have seen in Cord, if I go back here, you see that there is a virtualized infrastructure in Cord, and today they use OpenStack. Right? As it happens with Cord, they use OpenStack Kilo, which is about 2.5 years old. It's a fairly old OpenStack distribution. It would be great if they could move to a much recent distribution. But what happened with OpenStack, the default vSwitch, the Open vSwitch, basically is a kernel-based vSwitch. And we know that kernel-based switching has some performance limit. It's very, very flexible. It does everything, but at the cost of performance, of throughput performance, and latency and jitter. What we have been doing with ON Lab and other people is to try to enable, to enable the infrastructure to use a different Open vSwitch, to use a DPDK-based OVS. And this was enabled and also demoed at MWC 17, where we show, an order of magnitude throughput increase and a significant reduction in latency and jitter, right? But to do this, we had to backport a lot of functionality which are already available in the latest OpenStack distribution. We had to backport this to Kilo. So it's a lot of work, which maybe is not necessary, right, if we're able to move to the latest version. Some of the feedback we'd like to hear, and again, there will be a presentation Thursday morning of the Performance Brigade. Is in this brigade where some of this work has been done, right, to move from OVS to OVS DPDK. And we know that, for example, for L2 forward, layer 2 forward or layer 3 forward VM, we went from 200,000 packets per second throughput with OVS to about 3.5 million with OVS DPDK. So, significant performance increase. But we are still very far away from line rate, which at 64 bytes is about 10 million packets per second. So, one of the feedback we'd like to hear, do we need to enable PCI pass-through, VTD, or, known as SRIOV also, right? Is SRIOV required to be supported in CORD? And what does this mean, for XOS? What does this mean for the switching fabric, where some of the rules will be applied now? So it would be interesting to hear from people, if you like to achieve line rate, is it, very useful? Is it required? Or, is 3 million packets per second good enough today? So this is some of the feedback we'd like to gather. This will be presented Thursday morning, again at 9 a.m. We'll show you the detail, show you what of the, various work we did in all of these components, from the infrastructure, in compute node, in OpenStack, XOS, and the mass, basically the mass infrastructure to install this updated component, right? So, I'll summarize what we have done today. I can tell you what we'll do moving forward also. We have a functional EPC. It's a DPDK-based EPC, at least, on the data plane. Control plane works off, standard Linux interface today. However, we could also move it to a DPDK if we see the need, right? It operates in bare metal, virtualized environment. We'll show you Thursday morning in Docker containers. Right? Today it's fully orchestrated and operating also in a CORD environment. So with CORD, you can create EPC as a service, and you can see basically byte flowing through the control plane and the data plane. Right? Additional components. Again, today is the service and the packet gateway have been released. Additional component, MME, HSS, and PCRF, under the leadership of Sprint, will be made available over the next few months into CORD, right? So this pretty much the slide I had for you guys, but I'm open to any questions or what you want to know about the learning we had. Was it painful or easy?
Yeah, so we have about 10-15 minutes for Q&A. So please, if you have any questions for please go.
So Christian, I know that we're adding the S gateway functionality into this code, so that we can act either as a home network where maybe the visited network is somewhere else, and or vice versa. We are the visited network and we're actually not. Have you considered that? In referring back to your slides, really, I think it's the second one, right, where you showed the vRouter. Have you guys done any considerations there yet as to those new features? I know we're talking about stuff that's happened in the last week or so.
Yeah.
With this, and could you tell us that? And then the follow-on question is, I know we also have some IoT features, particularly S11U coming in.
Mm-hmm.
With that, and have you thought about some of the considerations there? Because that is one of those weird things about S11U, right? Is it is from the SP gateway user plane up to the MME.
Right.
So have you thought through those at this
No.
point?
No, we have done, whatever we have available today, that's what we have implemented. But there is no consideration yet of, data downlink notification or some of this issue for IoT. None of these have been looked at this point, yeah. Yeah, the first goal was to make this, functional, and even today in code as, the orchestrated environment, not look yet at the performance, performance aspect, but that's some of the stuff we'd like to.
So, and then maybe then going back to performance, where are you at PPS-wise?
So for L2 forward at 64 byte packet, we're at about 3 million out of, the line rate would be 14 million packet per second, right? So there is still a lot of overhead, which is in the switch, the soft switch, right? So the goal, do we need to bypass the soft switch using SRIOV, or is 3 million good enough?
I guess maybe the bigger question is 64 bytes the inside?
Yeah, that's
I think with VoLTE, right, it's a bit higher, right?
Right.
We're sitting a little bit higher than that. And then when we start talking about 5G, maybe it's premature, right? As we start talking about that in V6, right? I do expect us to be better on the wireless side about making bigger packets.
Yeah, definitely. And that's one of the key points. Which, average packet size should we measure, right? I mean, I know today we're using about 380 or 400, right? Is this the right packet size to get the throughput? But yeah.
And that's what I'm worried about. I don't necessarily want to chase an unrealistic goal or an unrealistic tiny size. It's admirable, but it may be too academic, right?
Yeah, it's a lot, yeah. But that's often the question we're being asked, when we present, what's your rate at 64 byte? Because people,
Your user plane for the 7 gateway you're showing here is right now the actual payload is going to the VMs, right?
Yes.
So
Can you repeat the question to the people?
Yeah.
Christian can repeat.
He can repeat. No, that's okay. So I guess my question is, if we had some form of a fabric that you can keep the payload in the fabric, do you expect a lot of improvements? Because you're not really, you're just moving the control to the, and would Intel get upset?
Well, I don't know if. Yeah, by fabric, I guess maybe you're talking about offloading capabilities to some programmable switches or barefoot PIFO type of switches, or even FPGAs, right? Yeah, definitely. The least you hit maybe the CPU, the more you can do on a offloaded device, maybe the best performance you'll get, right? But you lose flexibility also on the other hand, right? So it really depends what you want to do, right? We're also looking at offloading portion of this, what makes sense. We started to do a fairly detailed cycle analysis of where we're spending cycles in the functionality and what could be offloaded to an accelerator, being FPGA or GPU or whatever is available on the platform. But again, each time you offload, it's great maybe for performance, but flip side is you lose the functionality and ease of use. Any other questions?
So for these, I'll go back. I hate going back to the 64 byte number, but was that using all of the features of the current NGIC, all the different rules and everything as well? And could you explain maybe a little bit of those?
For the performance? Yeah, all of them. Actually, the performance, the number was with L2 forward VNF, right? L2 or L3, right? With the EPC itself, today, we're reaching 1.6 million packets per second per core. So it's a little bit lower. Today, with the EPCs, the bottleneck is on the EPC itself. That's why we try to maybe optimize and raise this number higher, right? Yeah, I guess Sprint has showed some great result with the EPC, right, and showing some almost linear scalability in terms of performance as you add core to the EPC with one what we call worker core doing the pipeline processing from NCAP, DCAP, bearer mapping, metering, charge record, we achieve about between 1.6, 1.8 million packets per second per core. As you add core, you scale linearly. So with 4 cores, we had about, close to 7 million packets per second throughput.
But even there, right, we're doing a little bit more with looking into the header, doing billing, tying it to DNS records, child protections. And maybe back to Tom's question, do you see that being able to be portable over P4? All of those extra beyond just the NCAP, DCAP?
No, I don't think so, yeah. But, I mean, you don't have a lot of flexibility still with P4, yeah. You can extract some field and, make some quick lookup, but, or DPI. I know DPI is probably very important for you guys on some packet, right? So it's harder with offloaded solutions, right? Yeah, we have to pick and choose what to offload, what does make sense to offload. So you can keep.
In general, that's in cord when we talk about the fabric, not only in the M-cord case, but also we are thinking of there's a fast path where there's no CPU, there's no compute required. And in that case, you can just do it all in hardware through the fabric. But as soon as you need some computational, whether it's DPI, whether it's some policy enforcement, something, you need to get up.
Yeah.
I know, but we're service providers. We want it all. We want it fast, and we want it in very
And you want it free.
I will give.
I didn't say that.
I will give you all.
We'll talk cost later.
All right.
Okay.
Anyone else? We have a couple of more minutes.
Just a very quick question. The
Yeah.
current solution you have, does it support any charging interface?
Yes. Yeah, we issue charge records. We don't plug into OSS, BSS, and maybe Lyle here could describe, right? We issue charge record, and you can, browse and create your charge record, right? But yeah, we do issue charge records.
Okay, so that performance figure you mentioned is with charging.
Yes.
Yeah. Okay.
Yes.
So there's a single location now that we just refer to it as printing.
Yep.
In the straight download of NGIC, it will print to a CSV file, so it is human readable.
Okay.
Right.
Yep.
We do have versions of that where it can go off in other implementations and go to a formal charge trigger function.
Yep.
And there, if you're familiar with those interfaces, it's an RF event type as well as an RF session type, obviously depending upon the record state within DPD.
Okay. Interesting. Yeah, we'll ask more. Yeah.
Okay. One more? No? Okay.
Thank you.
Well, thank you for your time.